Hello everyone, welcome back to this video. So in this video we are trying to find about Poisson distribution and its properties, as we have completed the properties for binomial distribution and saw a few examples. So from this video onwards we'll be trying to find out Poisson distribution and its properties. So first of all, we need to know what is a Poisson distribution, how to define it, what is its PMF, and then again we will try to find out its expectation, different moments, and also its variance. So our topic today should be Poisson distribution. As the name suggests, Poisson distribution is same as the Poisson process, but Poisson process is a random process and this is just a discrete distribution. Now the PMF for the Poisson distribution is more like exponential one, so it is an analog to the exponential distribution in the case of continuous random variables. So random variable x following Poisson distribution can be modeled as follows. So the PMF for the random variable x when it follows Poisson distribution can be written as probability of x equals to k. Now the values that the random variable x takes in this case are from 0 to infinity. Obviously the natural numbers, and it's not a continuous distribution, because if it were then it would have taken all the real numbers between 0 and infinity, and then we would have to use integration in order to find all the probabilities, but it's a discrete distribution. We shall go on to find the continuous random variables very soon after this section, but let us just finish this first. So probability of x equals to k would be equal to e to the power minus lambda to the power k divided by k factorial, and the values would be from k equals to 0, 1, 2 and all the way up to infinity. Okay, now what is this lambda? This is the parameter of the Poisson distribution, right? So let me write down the parameter. Parameter here is poi of lambda, that's what we call. So the parameter is lambda and we call the distribution as poi of lambda, which is basically Poisson lambda, and we say that x follows poi of lambda and only then the PMF is like this. Okay, right. So when x follows Poisson of lambda, the PMF is given as I have shown above, but we first need to check it's a PMF. Now obviously since k is positive, since k is greater than equal to 0, lambda is greater than equal to 0, we have e to the power minus lambda to the power k by k factorial also greater than equal to 0, which is essential for the PMF. So the PMF must always be non-negative, right? So this condition is satisfied. Now total probability now total probability is basically probability of the whole sample space omega, which should be equal to 1, and we shall see how to find that. So we are going to sum over all the probabilities. So k equals to 0 to infinity, probability of x equals to k. Okay, Now this gives us sum k equals to 0 to infinity e to the power minus lambda to the power k by k factorial. And since e to the power minus lambda is a expression independent of k, where k is our summation variable, we can safely take this thing outside the summation indices, because this is just a constant and it will be multiplied with each and every term of the summation. So it's just a common it's just a expression which can be taken common basically out of the whole series, assuming that the series converges, which it does, which we can show. So we can write this as e to the power minus lambda summation k equals to 0 to infinity lambda to the power k by k factorial. Now how to evaluate this sum is a question, and we shall learn how to do so. Now I would introduce to you something called the Taylor series. Now Taylor series. So what is a Taylor series? For a function f of x, we have f of x equals to f of a plus x minus a into f dash a plus x minus a whole squared by 2 factorial into f double dash a, and so on all the way up to infinity, where f is from a certain domain to some subset u, which is a subset of R, and a belongs to D, and f is infinitely differentiable, which means that f has derivatives of all orders. Okay, that's what it means by infinitely differentiable. So if this happens and there is a and we can say that the a is inside the radius of convergence of f, only then can a function fx can be rewritten around a point a in its domain as an infinite series, right? So this actually gives you an infinite series for a function, but the special case of the Taylor series is called the Maclaurin series. So the Maclaurin series is something like this. It is expansion around the point 0. So it is expansion around the point 0. This means if f is differentiable at 0, then we can write fx equals to f of 0 plus x into f dash 0 plus x square by 2 factorial into f double dash 0, and so on, which can be written in terms of an infinite series as follows: n equals to 0 to infinity nth derivative of f at the point 0 by n factorial into x to the power n. So this is basically the Maclaurin series, right? And it has to do with the fact that f is infinitely differentiable. The function f is finite and bounded in a certain region where we are trying to find the infinite series in some interval, and also f is differentiable at the point 0. Only then can you find the Maclaurin series. Now we are trying to do that for the function e to the power x. Okay, so let us take f of x equals to e to the power x. Okay, then one thing that you know for sure for the function exponential or the e to the power x function is that its derivative is itself, right? The derivative of nth order would also be itself, right? Because it doesn't matter how many times you differentiate this function, it will give itself back. So the derivative of nth order is fnx is equals to e to the power x. So at x equals to 0 we have fn0 equals to e to the power 0, which is basically 1. Now the Maclaurin series is e to the power x, then should be equal to n equals to 0 to infinity fn at the point 0 divided by n factorial into x to the power n, right? But as we have found out, fn0 is 1 for all n. This gives us the infinite series n equals to 0 to infinity x to the power n by n factorial. And as it turns out, this series is converging for all values of x in the real numbers. So the exponential function is always converging for every value of x. It doesn't really diverge as long as x is a real number, or we say x is a finite number, right? So you saw this series, right? Now we go back to our actual sum where we are trying to find out this sum, right? Summation k equals to 0 to infinity lambda to the power k by k factorial. So we write down our sum here. Coming back to original problem, probability of omega should be equals to e to the power minus lambda summation k equals to 0 to infinity lambda to the power k by k factorial. Now as you can see here, this sum and this sum are the same, so it's just basically this sum is just e to the power lambda where x has been replaced by lambda, right? So this gives you e to the power minus lambda into e to the power lambda, which gives you 1. So the total probability is 1, which is proved. Therefore p of x equals to k is a PMF. Now once we have proved that it's a PMF, we can actually go forward and find out its expectation. So let's see. We can write that expectation, and you shall see why this is one of the special series, because of how the expectation and the variance turns out here and the higher moments fit in. So the expectation of the series. Okay, given PMF is, so I'm just going to write down the PMF here again. It's just e to the power minus lambda into lambda to the power k by k factorial from k equals to 0, 1, 2 and all the way up to infinity, right? So it's the expectation would be given by the expectation would be e of x equals to summation k equals to 0 to infinity k into probability of x equals to k. And this, obviously this definition is very well known to us because we have been using it a lot of times, but in order to evaluate this sum we again need to consider a few basic things we have learned in this lecture, like the manipulations. Of course, the Taylor series and the Maclaurin series are not the basic ones because they would require a bit of tedious work for you to understand them completely and use them to their fullest potential, but we can still make our way somehow like this. And as you remember, k factorial is just this, because k factorial just means that it is k into k minus 1 into all the way up to 1. Therefore k factorial is just k into k minus 1 factorial, right? So therefore expectation of x should be summation k equals to 0 to infinity e to the power minus lambda to the power k by k minus 1 factorial. Now, one thing we should remember about factorials is that 1 by n factorial equals to 0 for all n less than 0. Okay, so whenever n is a negative integer, the reciprocal of the factorial becomes 0, or in other words, the factorial itself is infinity. So this comes us to show that exponential of x has the terms. If we just write down the infinite series, it would be something like this. We can take e to the power minus lambda common, and we can see that it's the lambda to the power 0 by minus 1 factorial plus lambda to the power 1 by 0 factorial plus lambda to the power 2 by 1 factorial plus lambda to the power 3 by 2 factorial, and so on, right? This term being 0 because this term does not exist. So this becomes e to the power minus lambda into lambda to the power 1 by 0 factorial plus lambda to the power 2 by 1 factorial plus lambda to the power 3 by 2 factorial plus lambda to the power 4 by 3 factorial, and so on. We can take a lambda common here because as you can see, the minimum power of lambda is lambda to the power 1 here. So taking a lambda common, what we find is this: 1 by 0 factorial plus lambda by 1 factorial, lambda to the power 1 plus lambda square by 2 factorial plus lambda cube by 3 factorial. And if you write this part in the form of an infinite series, we can see that this is very familiar to us, because this just gives us summation. See, it starts from 0, so n equals to 0, goes up to infinity, so infinity, so it would be a n factorial here, and it would be a lambda to the power n here, right? But this is just e to the power lambda, right? This is just e to the power lambda. Then this gives you lambda e to the power minus lambda into e to the power lambda, and they cancel off to give you lambda. So the expectation is lambda. The expected value of the Poisson distribution is the parameter by which it was modeled, and now you can understand there is a reason why this was modeled as lambda. This is called the expectation of the Poisson distribution. So we shall continue the variance part and the higher moments in the next lecture. For now, let us understand up to this portion only in this video, and also check out Bretter's math app for more statistical tools and all the video lessons and lectures related to this topic. Thank you.